Hey everyone, welcome to the walkthrough for homework 3 and questions 4 through 5. So these two last questions on your homework are about Buckingham Pi. And we went over this in quiz section along with a lot of useful material. So please look back at the slides if you ever are confused in this video. So let's get started by always reading the question and identifying our variables. So first, we are going to be looking at the question. So it says fluid velocity of a flow measuring nozzle. So right away we have our first variable. It's presumed to be a function of the pipe diameter d, fluid density rho, nozzle diameter a, fluid viscosity mu, and pressure drop delta p, sorry. So what does this mean? It means that the fluid velocity, is going to be a function of the diameter, fluid density, another diameter, fluid viscosity, and pressure drop. So we know that we have this function with so many different variables, and the goal of Buckingham Pi is to use dimensionless parameters by combining some of these variables in order to reduce the number of variables we have in our function. So let's get started. The first step is always to identify our variables, which we just did. Now we want to find the dimensions that are related with these actual variables. So let's get started with that. So as I talked about in quiz section, an easy way to do this is to just create a table. So we're going to create a table with our dimensions. So we have M, L, and T. And now we have 6 variables, it looks like. So we're going to draw 5 lines, 3, 4, and 5. Great. Now we're just going to fill these in, starting with velocity, which is also a variable. It's a dependent variable, but still nonetheless a variable. Diameter, we have density, we have another diameter, we have viscosity, and we have change in pressure. Great. So now let's start filling out these columns and rows. And the thing is, it's really important to be accurate here. A mistake here can result in your entire answer being incorrect. So let's be really careful about filling this table in. And these all can be found in that quiz section. There's a table in there that shows all of these dimensions. So let's take a look. We have velocity. We know that is length over time. So we're going to write 0, 1, -1. We know diameter is a function of length. So 0, 0. And then rho, we know is 1, -3, 0. And we have, again, another diameter. So that's 0, 1, 0. And then we have mu, which is 1, -1, -1. And delta P is 1, -1, -2. If you're confused about how I got these values, please take a look at those quiz section slides. Great. And now the next step is to just follow our consistent pattern for addressing these kinds of questions. So we know first, NV is the number of variables. How many variables do we have? We have 6 variables. Great. And then now we want to see how many dimensions do we have? Well, we have mass, length, and time all present, so we have 3. Great. Now we want to find the number of dimensionless groups parameters that we're going to be using, and we determine that using NV minus ND. And 6 minus 3 is going to be 3. Great. So as we know, this is going to be also the number right over here. We know ND and NV minus ND, we're going to have 3 core variables. And that also means we're going to have 3 dimensionless groups, and that's determined by right here and right here, right? Great. So now let's determine our 3 core variables and our 3 dependent variables. So right away, let's remember some of our rules. We know that if we're trying to find velocity, right, that's always going to be a dependent variable. That's always the case. And then now let's look for actually some similarities. This is where the table comes in handy. So right away we can see these are equal. And what is our rule when we have something equal like this? That means we have to put one of these variables in the core variables and another in the dependent variables. We can't have them in the same category. So in this section, I'm going to use diameter of the pipe as a core variable, and then I'm going to put the nozzle diameter as a dependent variable. Hope we're all following so far. Now let's take a look at what other ones we can relate. So we have velocity here, we have length and time. That means we need to have something that has length and time or a combination of both that can get us those. So in this case, I'm just taking a quick look, and it looks like we have rho and mu, and we have delta P. And it looks like right away we're going to just use mu, which has length and time, and we also have rho, which can cancel out that that mass term right there that's determined by the mu right over here. So we need to get rid of this, and we can use that to kind of get the right parameters for velocity. Great, so we're going to do that. We are going to put mu and rho right here in our core variables. That leaves us with delta P as a dependent variable. Great, so now that we've just grouped our variables, now we're going to actually write out our dimensionless groups. And if we remember how to do that, that's going to be using our capital Pi, and then we have our dependent variable, and then it equals our dependent variable times our core, and they're all going to be raised to the power A, B, C, and then we do that again for all the other dependent variables. All right, so this is dependent 1, this is dependent 1, then we do that for 2 and 3. So let's actually just take a quick look and write all of these out. So we have pi, I'm going to just write V equals V times, and we have our core variables, I'll use a different color, D, rho, and mu. Great, and then we have A, B, and C. Great, and then we're going to repeat this process for the other core variables, or sorry, other dependent variables. A, D times rho times mu, then D, E, F. Great, and then we have pi. Looks like our last dependent variable is delta P times D mu, or sorry, D rho mu, and then we have G, H, I. Notice I used all different variables for the exponents, and this is key. We cannot reuse it. We don't want to get confused. We want to keep it as straightforward as possible. These will not, A will not equal to D. That is not true. So let's keep going. I'm actually going to work out one of these for you all, but I do want you to attempt the rest of the other two. Great. So let's actually write out what that looks like. So we have pi V equals. So now what we're going to do is we're going to actually write out those dimensions. So we're going to take a quick look out here. V is L to the 1 power and T to the -1 power. So we're going to just write that out right here. L, 1, T, -1. Then we have, what's our next one? Well, we have L, which is for D, L to the 1, and that is to the A power. Then we have, for rho, we have M to the 1, L to the -3, that's to the B power. And then we have M to the 1, L to the -1, T to the -1, and that is to C power. Great. So the next step always is we know that this is a dimensionless parameter. That means it's going to be equal to M0, L0, T0, right? And now the goal of doing so is to combine all like terms. So let's start with our M. We have right over here 1, but then times B, so that's just B. MB, And then same thing here, C1, so that's plus C. Pretty simple, right? Now we'll do the same thing for L. We have L1 over here, nothing over here. So that's just 1. And then we have 1A right over here. So that's just plus A. Then we have negative 3B minus 3B. And then we have minus 1 and C right over here. So that's minus C. So that one's a little bit trickier. Then now let's do time. We have negative 1A minus A. Oh, sorry. Minus 1. There's nothing here. So it's good to just keep double checking as you're going. Then we have minus 1 C. So minus 1 minus C right here. Great. So now what? We want to determine A, B, and C. So we know how the dimensionless parameter that we found right here, how these terms actually relate right over here, how they actually relate. That is our goal. Remember in class, we worked on an example and I told you what that relationship was, but we're trying to now determine it ourselves. So let's keep going. That means we know B plus C is equal to 0. This has to be equal to this, right? And this has to be equal to this, and this has to be equal to this, right? So B plus C is equal to 0. And we have 1 plus A minus 3B minus C is equal to 0. And then we have minus 1 minus C is equal to 0. Well, that makes it easy. We have C is equal to negative 1. Then we have B is equal to negative C, right? That means B is equal to 1. Then now we have A is equal to 3B plus C minus 1. And then we have, that means A is equal to 3 minus 1 minus 1. That brings A to 2. Great, now let's put it all back into our expression. We have big pi V is equal to V, right? And what did we write over here? We wrote D times rho times mu. And we have A, B, C. Now, essentially what we're doing is we're going to plug in for A, B, and C. So for A, we have, sorry, I said 2 over here, but that is actually a 1. Sorry about that. So D is going to be 1, B is 1, and C is negative 1. What does that mean? That means the dimensionless parameter, our first one out of 3, is going to be equal to V times D times rho divided by mu. And here is your first dimensionless parameter. And you're going to repeat this for the other 3. So next, you should have what is A and what is delta P? You're going to find that. And that is what you're doing for question 4. Keep in mind that if you change the order in these, you will have different A, B, and C's. But in the end, your answer should still be the same. It doesn't matter which direction. If rho comes first, or D comes first, or mu comes first. In the end, just please stay consistent. Please stay consistent throughout these kinds of questions. Great, now let's move on to the next question. All right, so let's get started with question number 5. So with question number 5, we're going to always start by reading the question and finding our variables. So we have a biomedical device using a stirrer to mix the specimen. And to design the device, we need to know the power. There's our first variable. And power is a function of, first we have diameter, we have number of rotations, we have specimen viscosity, and specimen density. And now it's asking us first, the power consumption was found to be proportional to the square of rotation speed. Great. And now, by what factor would the power be expected to increase if the device needs to scale up and the diameter of the stirring impeller was doubled. Great, so let's get started with that first part of the question. We need to first obtain the relationship. That's always the first step. So let's get started. We know that power, denoted by P, is a function of, we have diameter, capital D, we have number of rotations, I'm going to denote that by capital N, we have viscosity, which is mu, and we have density, rho. So let's keep going. Let's do the same exact thing that we just did in the previous question. We're going to make our little table. It's very handy. And it looks like we have 1, 2, 3, 4, 5 variables. M, L, and T. Now we have power, we have diameter, we have number of rotations, we have mu, and we have rho. And so same as the last one, please try to fill this out, pause the video, and when you're done, unpause it and let's check. So power, we have M is 1, length is 2, and time is -3. Diameter, we know it's length, 0, 1, 0. The number of rotations is of defining frequency, right? Frequency is just time -1, so 0, 0, -1. Then mu, we have 1, -1, -1. And then we have rho, 1, -3, 0. Great. And let's just keep going with what we do know. So we know the number of variables is 5. We know the number of dimensions is 3. We know the number of dimensionless groups we need is 2. So let's define our core. We have 3. We have dependent. We have 2. Now we need 3 variables that define the core. We need 2 variables that define dependent. So we always know, let's start again, power, we know is going to be a dependent variable because that's what the function defines, right? So we have power, then what else do we have? Well, let's just take a closer look over here. And it looks like we don't have any similar ones that have the same dimensions. So can't use that rule, but let's just take a look. Power wants all 3 dimensions, right? And we have all 4 to choose from, right? So let's pick a combination that makes sense. So we have diameter, right? Use diameter. Then we can also use number of rotation. Sure, it has length, and now we have time as well. That's great. And now we have mu and rho. So let's just take a closer look. So we have mu right over here. Mu can be used as, let's take a look. We can use rho as a core variable. We can use mu as a dependent variable. Hope this makes sense. Also, another option is that if we actually define this in a different way, we can also use a different color. We can use diameter N and mu. Actually, no, sorry about that. We can use diameter, mu, and rho. That makes sense. There we go. So now we have things covered in all 3 components. So another way would be to use diameter, mu, and rho as your core variables. And that would mean 0, 1, 0, 1, -1, -1, 1, -3, 0. So we have, yes, we can somehow eliminate these 2 and we'll have this component still. So we are good. So that is another way to approach this question. For now, for the rest of this video, I will be using this, but I just want to let you know that this also is another way, and that means n would also be your other dependent. So I do want to show you that there are other ways to do this. I just say, please stick with one, make sure it follows the rules. As long as you follow the rules of Buckingham pi, you should be fine. So let's just keep going with this method right over here. So I'm actually gonna delete this as well. Great. So let's keep going. We know we need to find two relationships, D to the A and rho, A, B, C. And we have N, sorry, we have mu is equal to mu times D, number of rotations, rho, and we have D, E, and F. Great, so now we need to continue that same process that we just did. I'll just do one of these for you, I'll do that one, but you need to also do this one as well. So we have pi P is, now let's just take a look at P. We have, I do actually want to use different ink. It's equal to M1 L2 T minus 3. Let's double check that, great. Then now we have diameter, L. And then we have A. And then we have to be very careful here that we're copying everything over correctly. And then D, just a D, we have N, which is T to the negative 1, it's B. And then what do we have? We have C, which is rho. Rho is M to the 1, L to the negative 3, and then C. So again, we just need to combine our like terms and solve for A, B, and C. So we have M0, L0, T0 equals M, and we have to the 1, and then what else do we have? We have 1 and C, so plus C. We have, sorry, not plus, times L, then we have 2, then we have 1 and A right here, plus A, and then we have minus 3 and C, so minus 3C. Great. And then now we have T, we have minus 3 with nothing, okay? We have minus B, negative 1 times B, and then I believe that is it. So we have all of these, and now we just need to solve for A, B, and C. So I'm actually gonna do this on the next page right here. But we have 1 plus C equals 0. We have 2 plus A minus 3C equals 0. And we have minus 3 minus B equals 0. So right away, very easy. C is equal to negative 1. B is equal to negative 3. And now that means A is equal to 3C minus 2. That means A is equal to 3C is negative 3 minus 2. A is equal to negative 5. Okay, so that means if we go back up here, we have pi P power equals power times D times N times rho. Then now we put in those A, B, and C's. We have A, B, and C, right? So we're going to put it in for each one. A is equal to negative 5, N is equal to, sorry, negative 3, rho, we have negative 1. Negative 1, okay. So that means this dimensionless parameter is going to be power times 1 over D to the 5, N to the 3, and rho to the 1, rho, right? So here we have our first parameter, And we can just move this over, P. There we go. And that's one of your parameters, right? Your dimensionless term. Great, and then you're going to do the same thing for our other one, which we said was mu. So find mu, right? So that's that second, and we need to find both of those. Now let's take a look at the question. It says now power consumption is proportional to the square of the rotation speed, right? So that means by what factor will the power be expected to increase if the device needs to scale up and the diameter of the stirring impeller is doubled? So let's go back down. We know the power is proportional to the number of rotations squared, right? Great. So the next thing to do is relate our dimensionless terms. So we know this, and after you figure out mu, you'll know this, right? And now there is some coefficient k and some exponent n that relates these two together. Also, if you did it the other way, if you used n, right? So I'm going to backtrack and say, if you did the other way, remember we said p and n are dependent, right? We know right away that it also is related. And the k doesn't really matter too much here. We're really focused on that exponent. We really care about this exponent right over here, not the k. K is just to show that there is some k that relates these two, right? It's just a coefficient. So I'm going to actually erase this, and we're going to keep going with just this example right over here to stay consistent. So we have our pi p, right? Our Buckingham pi dimensionless parameter to be p over d5 n3 and rho, right? And now we have it equal to some k, doesn't really matter too much, some k, and then you're going to input this value, right? Which will also have what? It will also have these terms. It will have some form of d and n and rho, right? That's a great thing. And then we have n, right? N matters. So now we need to find the n, right? Which we actually, let's keep going. I will erase this. And essentially, you're going to plug this in, and you will find n. Find what n will relate these two. All right. Then what's going to happen is you are going to solve for p. After you solve an n, then you're going to actually have your answer in terms of p. And it will have, sure, it will have the k, not really too relevant. But the great thing is you're going to have d to the something, n to the something, and rho to the something. Okay? And the great thing about that is now, what is n? N is the number of rotations, right? And actually, we have d, we have diameter, and we have rho, which we have density. So what did the question ask? It asked what happens, right, to the power when what? When D doubles, right? So that means we know, we can use this relation. The new power, let's say new power, right? And this is old power. We actually know that the relationship between these two is going to be the difference between the old and the new diameter, right? And we know that this doubles, right? So that's 2, right? But what is the actual relationship, right? And that is determined right here, right over here. Whatever you get over here is going to be the same thing you input right here, the same value. Then essentially you're going to have your answer is going to be 2 to some number that you determine, and that is your final answer right over here, whatever number you determine, okay? So if you have any questions about this, please just send me an email. I will definitely be available to help today. I do want you all to figure this out. That's why I kind of left it in this form. But essentially remember, find N, rearrange for P, and then with that star number you find, you're going to just use it right over here to determine what happens to P when the diameter doubles. Great, I hope this was helpful. Please email me if you have any questions. I'm more than happy to help, and we'll see you very soon. Bye.